Have you ever wondered if you could see the world differently? I mean, not just with your eyes, but really understand it on a whole new level? Well, today, we're going to learn how to see the world like a physicist by unlocking the secrets of light itself. But hey, this isn't just about seeing pretty rainbows. For hundreds of thousands of aspiring engineers in India, mastering this stuff, ray optics, is a huge deal. It's a massive part of the Joint Entrance Examination, or JEE, which is one of the most competitive science exams on the entire planet.
Yeah, check this out. Over 5%. That one number tells you everything you need to know about the stakes here. 5% of the entire physics exam is dedicated just to ray optics. You get this right, you're in a great spot. You get it wrong, and well, it could be the difference between making it and missing out.
So, let's start our quest, shall we? We're going to dive into the exact same concepts that challenge some of the brightest students out there. And the first step is just to get a handle on the absolute basics, the fundamental rules of the game of light.
Okay, our first puzzle is all about bending light. You've seen this a million times. It's called refraction. It's what happens when light goes from one thing to another, like from air into a glass of water. It's the reason a straw in a cup looks like it's broken, right? So let's see if we can solve a classic problem with it.
Here's our challenge, and this comes straight from a JEE prep source. You've got a beam of light hitting a skinny little 5-degree prism. We also know its refractive index, which is just a fancy way of saying how much the glass slows down and bends light. So the big question is, what's its path going to be? And what angle does it come out the other side? To figure this out, you need a special key.
And that key is Snell's law. This one elegant formula is basically the master rule book for refraction. It connects everything: the angle the light comes in at, the angle it bends to, and the properties of the materials themselves. It's like the secret code that lets us predict exactly where the light is going to go every single time.
So how do we use it? Well, first, we apply Snell's law right as the light enters the prism. That tells us how much it bends inside. Then, we use a little basic geometry to figure out the angle when it hits the second side. Then, you guessed it, we use Snell's law one more time as the light leaves. And boom, we get our answer, 7.5 degrees. It's just a logical, step-by-step process.
All right, so we've mastered bending light. Let's move on to our next puzzle. How mirrors and lenses use these very same rules to create images. Or, some pretty convincing illusions.
Okay, take a look at this. We've got a concave mirror, kind of like what you'd find in a makeup mirror or a telescope. A ray of light is coming in, and it passes right through the focal point F. So, when it hits that mirror and bounces off, where's it going to go? Path 1, 2, 3, or 4? What do you think?
Well, the answer comes from a super simple, beautiful little rule of physics. For a concave mirror, any ray of light that goes through the focal point bounces off perfectly parallel to the center line, which means ray number 2 is our winner. It's that predictable. No guesswork needed.
Now, what's really fascinating is how similar the math is for mirrors and lenses. To figure out where an image is going to show up, we use these two equations. And I mean, look at them, they're almost identical. But there's one tiny, absolutely crucial difference: a plus sign for the mirror and a minus sign for the lens. Believe me, that one little sign changes everything. And these formulas solve other cool puzzles too. For instance, what if you have a lens that's curved on one side but totally flat on the other? Does it matter which way you point it? The math actually proves that, nope, it doesn't matter at all. A plano-convex lens is always going to act like a converging lens. The physics is just consistent. Okay, we've tackled prisms, we've figured out mirrors and lenses. Now for the best part. Let's connect all these rules to our final puzzle, the absolutely stunning light shows that we see all around us in nature.
So we've all seen a rainbow from the ground, right? It's that beautiful classic arc. But have you ever stopped to think, what would that same rainbow look like if you were, say, a pilot in an airplane flying high above the clouds and looking down?
The answer is pretty mind-blowing. You don't see an arc. From up there, a rainbow is a complete circle. A full, perfect ring of light. And if you're lucky enough to see a double rainbow, you'd see two complete circles, one inside the other. It just goes to show you, your perspective changes absolutely everything.
And this is where it gets really cool. Okay, what on earth could a radio signal bouncing off the atmosphere have in common with a mirage shimmering on a hot desert road? I mean, they seem like they're from completely different worlds, but they're both caused by the exact same physical principle: total internal reflection.
So this crazy thing happens when light is trying to go from a dense material, like water, into a less dense one, like air. If it hits the boundary between them at a shallow enough angle, anything past this critical angle, it doesn't go through at all.
Instead, it reflects back perfectly, like it hit a flawless mirror. This single idea is the secret behind fiber optics, those desert mirages, and even how radio signals can bounce all the way around the globe.
So, after this whole journey, bending light, making images, exploring all of nature's wonders, what's the big payoff? We've earned our reward, a toolkit of master keys. These formulas right here are the language physicists use to describe the world of light.
Here they are, the greatest hits. You've got Snell's law for refraction, the twin formulas for mirrors and lenses, the simple idea of apparent depth, and of course, the equation for that super important critical angle. These are the powerful tools that unlock basically everything we've talked about today.
And you know, these aren't just equations for an exam. These exact principles are running the camera in your phone right now. They're the reason the glasses on your face work. They are what's happening inside your own eye every single second. These are the silent, invisible rules shaping how you see reality. So the real question is, now that you know the rules, what will you see differently?